Welcome back. In this lecture I shall discuss various methods of producing low temperatures. The specific objectives of this particular lesson are to discuss methods of producing low temperatures using first sensible cooling, using endothermic mixing, using phase change processes, using expansion of liquids, expansion of gases, thermoelectric methods, and finally magnetic methods. At the end of the lecture you should be able to list various methods of producing low temperatures, explain the salient features of these methods, and explain the process of isentropic and isenthalpic expansion of liquids and gases and the practical significance of these methods. Let me give a brief introduction. First of all, let us look at the definition of refrigeration. If you remember, refrigeration is defined as the process of cooling of bodies or fluids to temperatures lower than those available in the surroundings at a particular time and space. Okay, that means the temperature of the system which is being refrigerated should be lower than the surrounding temperature. That is the major point to be noted here. Okay. And to achieve refrigeration, it is essential to produce temperatures low enough for heat transfer to take place from the system being refrigerated to the system producing refrigeration. So, let me explain this. Okay, let me draw the temperature axis here. Let us say that this is your temperature axis, and let this be the surrounding temperature, T surroundings. Let us say that we have a cold storage. Okay, this is a cold storage which is initially at the surrounding temperatures. Now we would like to reduce the temperature of this cold storage to a required level. Let us say that this is your required temperature. So the cold storage temperature has to be brought down from the surrounding temperature to this temperature. Okay, temperature is increasing in this direction. How this can be done? In order to do this, what is required is there should be heat transfer from the cold storage so that its temperature can reduce. Okay, so as you know very well, for heat transfer to take place, we must have another system which is in thermal contact with this cold storage and whose temperature is lower than the final required cold storage temperatures. Okay, that means let us say that we have a refrigeration system, okay, whose temperature T ref is less than the final cold storage temperature T required. Okay, so this is a, let us say that a cyclic device. If I bring this cyclic device in thermal contact with this cold storage, then there will be heat transfer from the cold storage to this refrigeration system. As a result, the temperature of the cold storage drops, and if the system is designed properly, the cold storage may finally settle at the required temperature. Okay, so this is our final required cold storage temperature. Okay. Now it is not enough that you just reduce the temperature of the cold storage to a required level. You also have to provide refrigeration continuously. Okay, that means refrigeration system is required first to reduce the temperature of a cold storage from that of the surrounding to that of the required temperature, and you also have to maintain the cold storage at that particular temperature. Okay, what do we mean by maintaining? We know very well that we don't have any perfect insulation in nature. Okay, and the moment you bring this cold storage temperature lower than the surroundings, there will be heat transfer from the surrounding to the cold storage. Okay, some heat transfer continuously takes place from the surrounding to the cold storage. If you do not do anything, then the cold storage temperature starts increasing. Okay, so if you want to maintain the cold storage at this required temperature, you must take out heat from the cold storage at the rate at which it is entering or at the rate at which it is being generated inside the cold storage. That means there must be continuous heat transfer from the cold storage to the refrigeration system. Okay, so this is Q out. Okay, that means heat transfer takes place from the surrounding to the cold storage because of this delta T, and this has to be taken care by extracting heat from the cold storage using a refrigeration system. Again, there should be some delta T temperature difference is required so that this heat transfer can take place. Okay. So finally the heat is coming to the refrigeration system, and if it is a cyclic device, whatever heat is coming to the refrigeration system must be thrown somewhere else. Okay, we will see that how it will be finally rejected. Okay, but what is important here is that we must be able to produce low temperatures using a refrigeration system. That means this temperature, okay, a low temperature or refrigeration temperature, such that the cold storage can be maintained at the required temperature. Okay, so this is an example of a cold storage, but any refrigerated space, for example an air conditioned space or a domestic refrigerator or anything, okay, what it involves is to produce low temperatures so that heat transfer can take place from the space that is being refrigerated to the system which is doing the refrigeration. Okay, and inside the refrigerant system we must be able to achieve low temperatures. Okay, so the topic of this today's lesson is how we can achieve these low temperatures. Okay, so let us look at some of the methods of achieving low temperatures. The various methods of producing low temperatures are sensible cooling using a cold medium, endothermic mixing of substances, phase change processes, expansion of liquids, expansion of gases, thermoelectric method and magnetic method. First let us look at the sensible cooling method. So producing low temperatures using sensible cooling using a cold medium. If a substance, let us say system A, is available at a temperature lower than the required refrigeration temperature, then by bringing it in thermal contact with the system to be refrigerated, that means system B, the temperature of the system B can be reduced. Okay, let me give an example again. Let us say that we have a building. Okay, we would like to reduce the temperature of the building, and at our disposal, let us say that we have a large body of cold water, okay, whose temperature is much lower than the surroundings, and I want to cool the building which is initially at the surrounding temperature. So when I bring the building in thermal contact with this cold water whose temperature is lower than the surroundings, heat transfer takes place from the building to the cold water, and in this process the temperature of the building reduces below that of the surroundings. That means I am able to produce refrigeration, okay, because I am reducing the temperature of the system to a level lower than the surroundings. Okay, so how this is happening? This is happening because of the sensible heat transfer between the building and the cold water. Okay, I have as I said, I have cold water at my disposal, so this is possible. And what happens to cold water during this process? During this process the cold water temperature has to increase. Okay, if it has a finite thermal capacity, since it when it absorbs heat, its temperature increases. That means during the sensible heat transfer process the temperature of the building reduces and the temperature of the cold water increases. Okay, so this is one of the simplest methods of reducing the temperature of a system. Okay, of course for this to happen continuously we must have a continuous supply of the cold water so that you can continuously provide the refrigeration. Okay, another example is use of cold air for reducing the temperature of air in a conditioned space. Okay, if you want to reduce the temperature of air in a conditioned space, you can supply cold air which gets mixed with the warm air inside the room and the temperature reduces. Okay, so here there are no latent processes, all the processes are sensible heat transfer processes. Okay. In the absence of heat losses, the heat transfer during this process, if let us say that over a time period, if Q is the heat transferred during this process, then Q can be written as Q is equal to MC into Tf minus Ti of A, that is equal to MC into Ti minus Tf of B. Okay, here A is a system that is providing refrigeration. That means in this example, A is the cold water and B is the building. Okay, whose temperature is getting reduced. So the heat transferred from the building in the absence of any losses will be exactly equal to the heat transferred to the cold water. Okay, and from this equation, if you know the thermal capacities of the building and cold water and their initial temperatures, and if I assume that the complete system, that means the building and the cold water attain an equilibrium, then you can find out what is the final equilibrium temperature. Okay, and as I said in this equation, Ti and Tf are the initial and final temperatures, M is the mass and C is the average specific heat of the system. Okay, so this is one simple way of producing low temperatures using a cold medium. Now let us look at the second method. Second method is producing low temperatures using endothermic mixing of substances. This is in fact one of the oldest methods known to mankind, and we know that, for example, from experience, let us say that you take a glass of water and if you add glucose to it or sugar, okay, then we know that if you add sufficient amount of glucose or sugar, the temperature of the water reduces, okay. That means the water temperature at the end of mixing will be lower than that of the surroundings, okay. Why this is happening? This is happening because mixing of glucose in water is an endothermic process. Endothermic process means heat has got to be supplied during this mixing process, okay. So this heat is supplied from the water itself. As a result, water temperature drops, okay. So as I said, mixing of certain substances produces very low temperatures due to the endothermic nature of the mixing process. And if you want very low temperatures, of course we have to use certain specific materials. For example, if you are dissolving sodium chloride salt in water, then you can achieve a low temperature as low as minus 21 degrees centigrade. And if you are dissolving calcium chloride salt in water, then you can get a temperature as low as minus 51 degrees centigrade. Okay, so this is one of the simplest ways of producing very low temperatures. But this method is not very practical as far as a practical refrigerant system is concerned, because it suffers from certain disadvantages. What are those disadvantages? The first disadvantage is that the refrigeration effect produced by endothermic mixing is typically small. Okay. So you cannot have very high capacity using this method. And second problem is that recovery of salt for reuse is very difficult. Okay, that means if you want to provide refrigeration continuously using this method, you have to have an infinite amount of salt at your disposal and an infinite amount of water at your disposal. Okay, which is not, which as you know is not possible. And if you want to recycle the same salt, then you have to separate the salt from the solution. Okay, which is very difficult. Right. So because of these two limitations, this particular method is not used in practical continuous refrigeration systems. Okay. Now let us look at the third method. Third method is the use of phase change processes. We know that low temperatures can be produced using substances that undergo endothermic phase change processes such as sublimation, melting and evaporation. Okay. So as you know very well, phase change means there will be a change of phase from either solid to liquid or solid to vapor or liquid to vapor. Okay. And these phase change processes, that means solid to liquid, solid to vapor and liquid to vapor, are endothermic in nature. Okay. That means heat has got to be supplied to the system undergoing these phase change processes. Okay. So during this process a large amount of heat can be transferred, right. Let me give some examples. For example, the latent heat transfer. Let us look at the amount of heat transfer during this process. For example, if I am melting water ice at 0 degree centigrade, then I can get a heat transfer rate of, or heat transfer of about 335 kilojoules per kg of ice. That means when 1 kg of ice melts at 0 degree centigrade, 335 kilojoules of heat is transferred. And the second example is sublimation of carbon dioxide at minus 78.5 degrees centigrade. When dry ice or solid carbon dioxide sublimates at this temperature, 573 kilojoule of heat is transferred per kg of solid carbon dioxide sublimated. And the last example is vaporization of ammonia at minus 20 degrees centigrade. That means when liquid ammonia vaporizes into gas at minus 20 degrees centigrade, 1330 kilojoule of heat is transferred per kg of ammonia vaporized. Okay, so these are typical examples and the typical temperatures. So one thing you can notice here is that unlike compared to the sensible heat transfer processes, here per kg of substance a large amount of heat can be transferred. Okay, so this is one of the advantages of this particular method. In addition to that, when we are using pure substances for phase change, the temperature remains constant during the phase change process. You know very well that water boils as long as you keep the temperature constant. Pure substance always boil or always condense at the same temperature. That means the heat transfer process is isothermal in nature. Okay, so this is another advantage of the phase change process. Okay. Now, so let us look at this method. First of all, both water ice and dry ice are widely used to provide refrigeration in several applications. Okay, we know that in many common this thing we use ice for producing refrigeration. For example, if you want to have cold water quickly, okay, you can add ice blocks to water. Okay, so that is the quickest way of reducing the temperature. And these methods are also used in some special applications such as transport refrigeration. Okay, especially solid carbon dioxide is used very widely in transport applications to keep the products cool. Okay, when you are using solid carbon dioxide, you can achieve temperatures as low as minus 78.5 degrees. So that means you can use this even for frozen food storage. Okay, so these refrigerant systems, that means there are systems which use ice or solid carbon dioxide, are known as expandable refrigerant system, because at the end of the process, normally the water or carbon dioxide gas is not recovered. That means the refrigerant gets expanded. Okay. Now, however, in actual systems, we do not really rely on solid ice or solid gas processes, but we use liquid vapor phase change processes, that means evaporation. Okay, why? Because evaporation is the most commonly used phase change process, because it is easier to handle fluids in cyclic devices. Okay, if you as you know, most of the common refrigerant systems are cyclic in nature. Okay, so in cyclic systems, it is much easier to handle a liquid or vapor rather than a solid. Okay, because transporting the solid around the cycle is difficult. Okay, so for this reason, in most of the systems we use evaporation and condensation. Okay. So for all phase change processes, the amount of refrigeration produced is given by Q is equal to m into delta H subscript pH, where Q is the heat transfer during the process, m is the amount of substance that has undergone phase change, and delta H pH is enthalpy change during the phase change. Okay. Apart from the latent heat, the temperature at which the phase change occurs is also important. Okay, because ultimately we have to produce low temperatures. Okay, so the amount of heat that is transferred is important. In addition to that, the temperature at which heat is being transferred is very important. Okay. And for liquid to vapor phase change, the normal boiling point is a good indication of the usefulness of a particular fluid for refrigeration applications. As you know very well, a normal boiling point is the saturation temperature at 1 atmosphere pressure. Okay, this is a good indication of the usefulness of any fluid for refrigeration purposes. Okay, for example, water has a normal boiling point of 100 degrees centigrade. That means at 1 atmosphere, its temperature is 100 degrees centigrade, which is way beyond the surrounding temperatures. So if you want to use water as a refrigerant, then you have to reduce the pressure. Okay, that means if a refrigerant system uses water, then it will be operating at pressures very much below the atmospheric pressure. Okay, so this is how the normal boiling point will tell you about the operating pressures. Now the latent heat of vaporization and normal boiling point are related by what is known as a Troughton's rule. The Troughton rule says that delta SFG, okay, delta SFG is nothing but the molar entropy of vaporization is constant for all fluids. That is what the Troughton rule is all about. Constant means not a single value, but it is found that this value for most of the fluids lies in this range. Okay, and what is this delta SFG? Using your thermodynamic relations, we can write delta SFG as delta HFG divided by TB, where TB is a normal boiling point and delta HFG is a molar enthalpy of vaporization at normal boiling point. Okay, so the Troughton rule says that the ratio of the molar latent heat of vaporization at normal boiling point divided by the normal boiling point in Kelvin is constant for most of the fluids. This rule is very interesting, and it is also very useful because you can derive certain things from this rule. For example, from this Troughton's rule, you can see that the latent heat of vaporization increases as the normal boiling point increases. That means as TB increases, delta HFG increases. And you can also find from this equation that substances having lower molecular weight will give rise to higher specific latent heat of vaporization. Okay, that means on per kg basis, the latent heat of vaporization increases as the molecular weight reduces. Okay, in fact, you can just compare, for example, water. Water has a molecular weight of about 18, and you compare this with any refrigerant whose molecular weight is much higher than the water, and you will find that at normal boiling point, the latent heat of water is much higher than latent heat of any other refrigerant with a higher molecular weight. Okay. Now, a refrigerant, as I said, should have low normal boiling point so that they vaporize at sufficiently low temperatures. Okay, as I said, if you want to have produce low temperatures at reasonably high pressures, then the normal boiling point should be low. However, if the normal boiling point is very low, then the operating pressures will become very high. Okay, that means a normal boiling point should lie within a certain range for the fluid to be useful in a refrigeration system. And the Clausius-Clapeyron equation relates the vapor pressures with temperatures, and it is given, you must have studied this in your thermodynamics, the Clausius-Clapeyron equation. This is given by d ln p by dt, where ln is a natural log, and p is the saturation pressure at any temperature T. So the slope of saturation pressure to temperature on a semi-log scale is equal to delta HFG divided by RT square, where delta HFG is the latent heat of vaporization at a particular temperature T. T is in Kelvin and R is a gas constant. Okay, so this you can see that relates the saturation pressure, temperature with the latent heat of vaporization. This is a very useful equation, and using this equation we can find out the latent heat of vaporization if you have the saturation vapor curve, right? Or you can find out saturation pressure at a given temperature, okay, from saturation pressure from a known temperature, and right. Of course, this equation, probably you remember, is derived based on the assumptions that the specific volume of the vapor is much higher than the specific volume of the liquid, and also that the specific the vapor behaves as an ideal gas. Okay, under these assumptions, this particular equation is derived. Okay, and this is derived from the Clausius equation. Okay. Now let us look at the expansion of liquids. When a high pressure liquid flows through a turbine delivering net work output, its pressure and enthalpy fall. Okay, so if you have a high pressure liquid at your disposal, okay, you can reduce the pressure of the liquid. That means you can expand the liquid in two ways. The first way is by using a device called as a turbine. Okay, so let us look at a turbine. So what does a turbine do? A turbine delivers a net work output. Okay, right. So if you are talking about a liquid, a high pressure liquid, okay, high pressure liquid at state 1 enters the turbine and it delivers net work output W net, and it exits the turbine at a low pressure. Okay, so low pressure liquid or low pressure fluid. Okay, we really do not know whether it is a liquid or vapor at this point, right. So you can reduce the pressure of the liquid using a turbine, and if you are applying, let us say I am taking the control volume across this one and I am applying, let us say, first law of thermodynamics, and if I am assuming that this process is a steady state steady flow process, then you can apply the first law of thermodynamics of a steady state steady flow process. And if I further assume that delta Ke, that means change in kinetic energy, and delta P, change in potential energy, both are negligible, then from the applying the steady state steady flow energy equation, you can show that if m dot is the mass flow rate of the liquid, then m dot into H1 minus H2 is equal to W net plus Q, where Q is any heat transfer from the turbine. Okay, if the turbine is adiabatic, then Q becomes 0, right, and W net is simply equal to m dot into H1 minus H2, or the specific work, that is the small W net, let us say specific work is equal to H1 minus H2, which is nothing but the difference in the enthalpies between the inlet and the outlet. Since W net is positive, that means W net is greater than 0, H1 will be greater than H2. Okay, that means the exit enthalpy will always be lower than the inlet enthalpy. And if you further assume that the specific heat of the liquid remains constant and liquid does not undergo any phase change during the expansion, then you can simply write H1 minus H2 is equal to Cp into T1 minus T2, right, which is greater than 0. That means T2 will be lower than T1, or the temperature of the liquid at the exit of the turbine will be lower than the temperature of the liquid at the inlet to the turbine. Okay, so expansion using a turbine always reduces the pressure, it always reduces the enthalpy. Okay, and it always reduces the temperature. Now the point is, what will be the temperature drop? Okay, is it substantial? On what does it depend? Okay, that we shall see in the next few slides. So in an ideal case, as I have already discussed, the expansion process can be reversible adiabatic. That means the process is reversible and there are no heat transfer from the turbine. That means it becomes an isentropic process. And for an adiabatic process, the drop in enthalpy is equal to the specific work output, as I have already discussed. And if you neglect delta K and delta P, that means kinetic and potential energy changes, then the specific work output is simply equal to H1 minus H2, where H1 and H2 are the inlet and exit enthalpies of the liquid at the turbine. Okay. Now, when a high pressure liquid is forced to flow through a restriction such as a porous plug, its pressure decreases. So, as I have already mentioned, there are two ways by which you can reduce the pressure of a high pressure liquid. One is by using a turbine and extracting useful output, and the second method is using a restriction. For example, restriction means it could be a valve. Okay, so let us say that you almost close the valve and force the liquid to flow through the valve, right? Then also its pressure drops, but you don't get any work output out of this, right? So one is using a turbine, the other one using a restriction. Okay, so let us look at this. In general, a restriction could be a porous plug, okay, or it could be a valve. Okay, valve means not fully open valve, it is a partly closed valve, right? When you have a valve and when this provides a restriction, you find that there is a pressure drop. Okay, that means P1 will be greater than P2. Okay. Now again, if you take a control volume across this, let us say I am taking a control volume across this, and I am assuming that this is adiabatic. That means there is no Q is 0. Okay, no heat transfer between the porous plug and the surroundings, right? And I also assume that potential and kinetic energy changes are negligible. Okay, then I apply steady state, steady flow equation to this control volume. So what do we get? We find that if m dot is again the flow rate of the liquid, m dot into H1 minus H2, okay, is equal to Q plus W. But we find here that there is no heat transfer, Q is 0, and then there is no work production, so W is also 0. Okay, so this implies that H1 should be equal to H2. Okay, that means the expansion using a restriction such as a porous plug or a valve leads to an isenthalpic process. That means the enthalpy of the liquid remains constant. Okay, of course you must keep the assumptions in your mind. Under these assumptions, the enthalpy of the liquid remains constant. Okay. So as I said, no net work output is obtained, and if the process is adiabatic, delta K and delta P are negligible, then H1 is equal to H2. Thus, this process, we normally call this process as a throttling process. So a throttling process is an isenthalpic process. Okay, whereas the expansion using a turbine in an ideal case is an isentropic process. Okay, so expansion in an ideal turbine is an isentropic process, whereas expansion using a throttling device is an isenthalpic process. That means in one case entropy remains constant, whereas in throttling case enthalpy remains constant. This is a very important difference and you must keep this in mind. Okay. Unlike expansion using a turbine, throttling is highly irreversible. That means entropy of liquid always increases during the throttling process. Now we are more interested in the temperature drop. Okay, so the temperature drop during isentropic as well as isenthalpic expansions depends on two things. One is the pressure drop, and the second one is the initial state of the liquid. Of course, it also depends upon the nature of the liquid. So if you are fixing the liquid, this depends on the pressure drop and the initial state of the liquid. Let us see how these two factors affect the temperature drop. If the initial condition is saturated liquid, then expansion, whether using a turbine or a throttling device, produces significant temperature drop due to flashing of some liquid into vapor. Okay, so let me explain this one. Okay, so as I said, let us say that this is the process 1 to 2. Okay, the expansion process. So initially we are at this point. Point 1 is your initial state, or at the inlet of the device. Okay, initial condition. So process 1 to 2. Okay, I have plotted this on TS coordinates. Okay, so during process 1 to 2, entropy remains constant. So this is an isentropic process expansion. That means process 1 to 2 is the process in an ideal turbine. Okay, and process 1 to 2 dash is an isenthalpic expansion process. That means H1 is equal to H2 dash. So this process 1 to 2 dash is an isenthalpic expansion. That means this is the process that occurs in a throttling device. Okay, that means 1 2 stands for a turbine, ideal turbine. 1 to 2 dash stands for an isenthalpic expansion in a throttling device, right? And as you can see that the initial condition lies on the saturated liquid region. That means initial state is saturated liquid. Now as the process takes place, the pressure drops, and let the 2 or 2 dash be the final condition. You find that at the final condition, whether it is 2 or 2 dash, the nature of the fluid is not liquid, but it is a mixture of liquid plus vapor. Okay, so at the inlet to this turbine or throttling device, we have a saturated liquid, but at the exit we have a mixture of liquid plus vapor, right? That means during this process some of the liquid got converted into vapor, okay, or some of the liquid flashed into vapor. Now we know that this process is a phase change process. That means liquid has become a vapor, and this is an endothermic process. That means heat must be supplied or energy must be supplied. Okay, and since we are assuming that the turbine and throttling device both are adiabatic, that means there is no heat transfer from the surroundings to the system. So whatever heat transfer has taken place must be from within the system, right? Only then vaporization or flashing can take place, right? So when some liquid flashes into vapor in an adiabatic device like a turbine or a throttling device, then the temperature of the rest of the fluid has to reduce, because it has to supply the energy required for the vaporization. Okay, as a result the temperature of the entire system reduces. Here the system means the fluid which is undergoing the expansion. Okay, so you must keep this in mind. The significant drop in temperature is taking place because during the expansion process vapor is being generated. Okay, and the energy required for vapor generation is supplied by the liquid itself. As a result its temperature drops, right? So this is the principle. Okay, so you can see that P1 and P2 are the initial and final pressures, and P1 is greater than P2. So for a given pressure drop, this is the temperature drop, okay, delta T. Okay, you can see that temperature drop is significant as long as the initial condition is saturated liquid and the final condition lies in the two phase region. Okay. Now as I said, if the initial condition is saturated liquid, then expansion produces significant temperature drop due to flashing of some liquid into vapor. Another thing I would like to point out is that the temperature drop, so this is the temperature drop. The temperature drop is same whether you use a turbine, that means whether you use a process 1 to 2 or 1 to 2 dash, right? That means for the given pressure drop, the temperature drop will always remain same irrespective of the device. That means irrespective of whether you are using a turbine or a throttling device, as long as the final condition lies in the two phase region. Okay. Now if the initial condition is subcooled, so we have considered the case of where the initial condition is saturated liquid. Let us say, what if the initial condition is not saturated but it is subcooled? Okay, so that the exit condition is liquid, then we find that the temperature drop due to expansion is small. Okay, again let me explain this one. Okay, for the same pressure drop P1 to P2, now the expansion is taking place not in the saturated or vapor dome region, but it is taking place in the liquid region itself. That means here. Okay, so I have magnified this. You can see that this is again P1 and this is again P2. now the expansion process is taking place, and the expansion process in a turbine is of the liquid is given by 3 to 4, and the expansion process in a throttling device is given by 3 to 4 dash. Okay, so the dash line is for throttling, the solid line is for expansion in a turbine. So compared to this temperature drop, okay, you can see that for the same pressure drop, the temperature drop obtained here is very small. Okay, for example, if I am talking about expansion in a turbine, this is the delta T in the liquid region. Okay, so you can see that this delta TL is much smaller than delta T in the two phase region. Okay, and another thing you can see here that the delta T gets reduced further if you are replacing the turbine by a throttling device. Okay, so this delta T, which is the temperature drop produced when you are using a throttling device in place of a turbine, is much smaller than the temperature drop that you would get when you use a turbine. Okay, that means there are two changes compared to the earlier case. First case is that the magnitude of the temperature drop for the same pressure drop is very much reduced now, and unlike the previous case, here the nature of the process also affects the temperature drop. Okay, if the temperature drop takes place in a turbine, it will be slightly higher compared to the temperature drop that takes place in a throttling device. So as far as the refrigeration system is concerned, we find that expanding the liquid only in the subcooled or compressed liquid region is not of much use, because we are not really able to produce very low temperatures, or we are not able to produce large temperature drops. Okay, so normally in all refrigeration systems, low temperatures are produced by flashing some of the liquid into vapor. Okay, so that's how we get low temperatures, right? So we will come back to this when we discuss the practical refrigerant systems. Now let us look at the next method of reducing the temperature, that is by using expansion of gases. Now similar to liquids, gases can also be expanded from high pressure to low pressure, either by using a turbine. That means either you can use an isentropic expansion using a turbine and get net work output, or you can also use a throttling device. That means an isenthalpic process. Okay, so just like liquids, you can reduce the pressure either by using a gas turbine or either by using a throttling device, right? But there is an important difference. Temperature of the gas always decreases during isentropic expansion. That means just like liquids, when I am expanding a gas using a turbine, its temperature always reduces. Okay, so in this aspect it is similar to a liquid, right? But when it comes to throttling, whether temperature decreases during throttling or not depends on the nature of the gas and its initial state. Okay, so whenever you are throttling a liquid, we know for sure that the temperature of the liquid reduces. Okay, the amount of reduction may not be significant, but temperature always reduces when you are throttling a liquid. But when you throttle a gas, whether the temperature decreases or not depends upon the nature of the gas and also depends upon the initial state of the gas. So you cannot say offhand that throttling of a gas always reduces the temperature. Okay, now let us look at this in some detail. Throttling of gases. First let us look at an ideal gas. If you throttle an ideal gas, what happens? Throttle means, as I said, reducing the pressure using a restriction. Okay, so that you must keep in mind. So when I am throttling the gas means when I am reducing the pressure of the gas using a restriction. So when I am throttling an ideal gas, as you know, the throttling process is an isenthalpic process, and for an ideal gas the enthalpy is a function of temperature only. Okay, so during the throttling process enthalpy remains constant, right? That means temperature also has to remain constant as long as the gas behaves as an ideal gas. Okay, that means throttling of an ideal gas does not reduce the temperature. In fact, the temperature remains constant because the enthalpy remains constant, and the enthalpy of the ideal gas is a function of temperature only. Okay, so this is point number 1. Next, when we come to real gas, okay, so in case of real gases, whether the temperature decreases or increases depends on a property of the gas called as Joule-Thomson coefficient. Okay, this is very, very important, and probably you have studied this in your thermodynamics. So Joule-Thomson coefficient, say it is symbol is mu subscript Jt. It is given by mu subscript Jt is given by dou T by dou P at constant enthalpy. Okay, that means partial derivative of temperature with respect to pressure along an isenthalp or along a constant enthalpy line. So this is the definition of Joule-Thomson coefficient. From thermodynamic relations, we can show that Joule-Thomson coefficient mu Zt is equal to T into dou V by dou T subscript P minus V divided by Cp, where Cp is the specific heat of the gas at constant pressure, V is the specific volume, T is the absolute temperature, and dou V by dou T subscript P is the slope of isobar in a volume temperature diagram. Okay, so this is the expression for Joule-Thomson coefficient, and you can easily see that for an ideal gas which obey the equation PV is equal to RT, okay, you will find that mu Joule-Thomson coefficient is 0. Okay, so you can just check that because dou V by dou T into T works out to be V, right? So V minus V becomes 0. Now temperature, from this equation you can easily see that temperature decreases when mu Zt is greater than 0 and temperature increases when mu Zt is lower than 0. Why? Because we have seen that this Joule-Thomson coefficient by definition is equal to dou T by dou P at constant H, right. So during expansion process pressure reduces, that means dou P will be negative. Okay, so if temperature also reduces, then dou T also will be negative. Okay, that means Joule-Thomson coefficient will be positive, right. So for gases whose temperature reduced during throttling, the Joule-Thomson coefficient has got to be positive. If the Joule-Thomson coefficient is negative, that means dou P is negative, so dou T has got to be positive. Dou T is positive means temperature at the end of the throttling device will be higher than the temperature at the inlet to the throttling device. Okay, that means temperature increases. Okay, so from this you can say that when mu Zt is greater than 0, temperature decreases, and when mu Zt is less than 0, temperature increases. And it can be shown that throttling produces low temperatures when the initial condition is on the left hand side of what is known as an inversion point. Okay, so let me describe the inversion point. A small experiment, let us say that we have a gas, okay, it flows through a pipe, and we put a valve in between, right. So let this be the inlet condition and this is the exit condition. At the inlet, let the temperature and pressure and temperature be P1 and T1. So for gas is flowing through the system, and let's assume that it is perfectly insulated and all that. So by closing the valve, what I am doing is I am forcing the gas to undergo a throttling process. Okay, so what I do is I measure the exit pressure and temperatures, right. So to start with, I keep the pressure and temperature at the inlet constant. Okay, so once you fix the pressure and temperature of the gas at the inlet as constant, the enthalpy is also fixed. Let's say that enthalpy is this. Okay, so the enthalpy at the inlet to the throttling device, which is nothing but the valve here, is fixed. Since this is an isenthalpic process, exit enthalpy will also is also fixed, and that is nothing but inlet enthalpy. Okay, H1 is equal to H2. So what I do is I close the valve to a certain position, and I measure the exit pressure and temperature, and I put one curve. Put one point on temperature pressure chart. Okay, so let this be my initial state before throttling, and I close the valve and I find that pressure and temperature at a certain valve position are this. Okay, then keeping the same inlet conditions, I close the valve further. Okay, and again I measure pressure and temperature, and I find that the pressure and temperature are lying at point F2. Okay, if I go on varying the valve position, I can generate a series of points. Okay, pressure and temperature, and if I join these all these points, I get a curve of this nature. Okay, this curve has a point of inflection at F3, and this point is known as inversion point. This is very important, because you can see that to the left of the inversion point, as the pressure is reduced, that means as the gas undergoes throttling, the temperature is actually increasing. That means the Joule-Thomson coefficient is negative to the left of the inversion point, whereas to the right of the inversion point, as the pressure reduces, the temperature is also reducing. Okay, that means the Joule-Thomson coefficient is positive to the right of the inversion point and negative to the left of the inversion point, and on the inversion point obviously the Joule-Thomson coefficient is 0. Okay. Now I can carry out this experiment by varying the inlet conditions. Okay, so let us see what happens if I do that. An inversion curve is I can obtain by joining the locus of all the inversion points. Okay, that means what I do is I vary the inlet conditions and I carry out the throttling processes at different enthalpy lines. Okay, so you have different enthalpy lines H1, H2, H3 like that, and each enthalpy line has an inversion point. And when you join all these inversion points, you get what is known as inversion curve. So this dashed line is called as inversion curve, and this inversion curve intercepts the temperature axis at a particular temperature, and this temperature is known as maximum inversion temperature. Now you can see that to the right of within this inversion curve, within this region, you have what is known as a cooling zone, and in this zone the throttling always reduces temperature. That means Joule-Thomson coefficient is always positive inside the inversion curve, and outside the inversion curve you have a heating zone. That means Joule-Thomson coefficient is always negative. That means if throttling takes place outside the inversion curve, temperature always increases during throttling, whereas temperature always reduces during throttling when throttling takes place inside the cooling zone. And what is the significance of this maximum inversion temperature? You will see that when throttling takes place, when the initial temperature is higher than the maximum inversion temperature, that means throttling is taking place in this region, you find that it always increases the temperature. Okay, so if you want to reduce the temperature of a gas during throttling, its initial temperature must always be lower than the maximum inversion temperature. This is a necessary condition for reducing the temperature during throttling. Okay, of course this is not sufficient condition. Okay. So the maximum inversion temperature has a physical significance. We find that for most of the gases, the maximum inversion temperature is much higher than the room temperature. So when you expand these gases by using a throttling device, their temperature drops. For example, nitrogen, air, carbon dioxide, etc. Okay. Of course, there are some exceptions like helium, hydrogen, etc., whose inversion temperature, maximum inversion temperature, is very low. That means very much lower than the room temperature. So when you expand or when you throttle a helium gas, then you find that its temperature increases. So if you want to reduce the temperature of a helium gas using throttling process, first you must bring the inlet temperature of the helium gas below its maximum inversion temperature. Okay. So let me just summarize. The point where the inversion curve intercepts the temperature axis is called as maximum inversion temperature. For any gas, the temperature will reduce during throttling only when the initial temperature is lower than the maximum inversion temperature. For most of the gases, the maximum inversion temperature is above room temperature, hence throttling of these gases can lead to their cooling. The same thing can be indicated on a typical TS diagram. Let us look at the typical TS diagram of a fluid. Okay, and what does it tell us? So on this TS diagram, as you know, this within the vapor dome you have liquid plus vapor region in this dome, and above the vapor dome you have the single phase region. Okay, and on this TS diagram I have shown isobars, that means constant pressure lines P1, P2, P3, P4, and P1 is greater than P2 is greater than P3 is greater than P4. Okay, and I have also shown constant enthalpy lines. So these are the constant enthalpy lines. So throttling, as you know, takes place along the constant enthalpy line. Okay, and each constant enthalpy line gives me a point of inversion. Okay, so if I join all these points of inversion, I get what is known as inversion line, and on this inversion line the Joule-Thomson coefficient is 0. Okay, so if you look at this TS diagram, you can arrive at some important conclusions. First conclusion is that if throttling takes place above the inversion curve, the temperature always increases during throttling. For example, if I am throttling from P1 to P2, okay, so starting with this temperature, you find that temperature always increases. That is the first observation. Second observation is that for a given pressure drop, let us say that P2 to P3, the temperature drop increases as the throttling takes place at lower temperatures. Okay, so for a given pressure drop, as the throttling takes place at lower temperatures, temperature drop increases. So this is the second conclusion. Third conclusion is that okay, so third conclusion is that temperature drop becomes higher when throttling takes place at higher pressures. For example, if you look at this one, between P2 and P3, this is the temperature drop, but between P3 and P4, sorry, and between P2 and P3 the temperature drop is higher. If the throttling takes place, let us say from some pressure this one to P3, this temperature drop is still higher. Okay, so throttling at higher pressures provides higher temperature drop. So these are summarized here. At temperatures above inversion curve, throttling increases temperature. Maximum temperature drop occurs when the initial state lies on the inversion curve. All these conclusions are based on our TS diagram. Okay, throttling at low pressures produces smaller reduction in temperature compared to high pressures. For a given pressure drop, the drop in temperature is higher at lower temperatures. And finally, gases cannot be liquefied by throttling unless the temperature of the gas is first lowered sufficiently. So in the liquefaction plants, what is done is the pressure of the gas is increased first, and then its temperature has to be reduced sufficiently so that when you throttle it, its temperature, exit temperature is such that the exit condition lies in the two-phase region and liquid is produced. Okay. Now let us look at expansion of gases using a turbine. So as I have already mentioned, temperature of a gas always decreases with a net work output. That means whenever you are expanding a gas using a turbine, its temperature always drops. However, the temperature drop decreases as the temperature decreases. This is unlike your isenthalpic expansion where the temperature drop increases as the temperature decreases, but in case of expansion of gases through turbine, the temperature drop decreases as the temperature decreases. Okay, this is actually a disadvantage. Actual process in a turbine can be adiabatic, but is irreversible due to frictional effects. And in practical liquefaction plants and all, a combination of adiabatic expansion followed by isenthalpic expansion is used to liquefy gases. So the adiabatic expansion is used primarily for pre-cooling the gas. Then the pre-cooled gas is expanded using a throttling device, so that the final condition lies in the two-phase region. Okay. Now let us look at thermoelectric refrigeration. Thermoelectric refrigeration is based on what is known as Peltier or reverse Seebeck effect. So what is reverse Seebeck effect? Suppose we have two materials, dissimilar materials A and B, and these two materials are joined. So we get two junctions, junction 1 and 2. Okay, and if you maintain these two junctions at two different temperatures, that means T1 is not equal to T2, then you find that an EMF is developed. Okay, because of this temperature difference. This effect is known as Seebeck effect, and this is the principle behind temperature measurement using thermocouples. Now the Peltier effect, this is the reverse of Seebeck effect. Okay, Peltier effect is reverse Seebeck effect. Here what we do is, initially the two junctions are at the same temperature, then we connect a voltage supply and pass current through this. So when a current passes through these two dissimilar materials, you find that at the junctions the temperatures will become different. So in this case you will find that T2 is lower than T1. Okay, so as long as the current is flowing through it, you will find that there is a temperature difference. So as a result, at T2 you can get refrigeration effect and heat rejection takes place at T1. Okay, so this is known as Peltier effect. The thermoelectric refrigerant systems are subject to 5 different effects. First is known as Seebeck effect, which I have already described. In the Seebeck effect, as I said, EMF is produced, and this EMF produced is equal to alpha into temperature difference T2 minus T1, where alpha is called as Seebeck coefficient or thermoelectric power. And the next effect is known as Julian effect. This is nothing but the generation of heat due to flow of current through a resistor. Okay, all these materials have resistance, finite resistance. So as the current flows through it, heat is generated, and this heat generation rate is given by Qzen is equal to I square R, where I is the current and R is the resistance. Third effect is known as conduction effect. When you are maintaining the junctions at two different temperatures, heat conduction takes place along the material, and this heat transfer rate is given by Q conduction is equal to U into T2 minus T1, where U is the overall thermal conductance and T2 minus T1 is the temperature difference. The fourth effect is the Peltier effect, which I have already described, and heat transferred during Peltier effect at each junction is given by Q is equal to phi into I, where I is the current and phi is the Peltier coefficient. Okay, and the last effect is known as Thomson effect. What is this effect? When current flows through a conductor in which there is an initial temperature gradient, temperature distribution gets distorted. Okay, as a result, heat transfer takes place, and this heat transfer rate per unit length due to Thomson effect is given by Q tau is equal to tau into I into dt by dx, where tau is the Thomson coefficient. Okay. So, it can be easily shown that a relationship exists between the Seebeck, Peltier and Thomson coefficients. And in practice, we do not use the pure metals because pure metals have high thermal conductivity, which is not desirable. What we require is a material having high electrical conductivity but low thermal conductivity. Okay, so metals are not used. We use semiconductor materials, P and N type semiconductor materials in actual thermoelectric refrigerant systems. And from a simple analysis, we can derive expressions for temperature lift, heat extraction and heat rejection rates and COP, okay, in terms of the design and material parameters. And it is also possible to optimize the current either for maximum temperature lift or for maximum heat transfer rates or for maximum system COP. So, the last effect is what is known as adiabatic demagnetization or magnetic effect. The magnetic refrigeration is based on the magnetocaloric effect discovered by Warburg in 1881. What is the principle of this? The principle of this is that paramagnetic materials raise their temperature when adiabatically magnetized and reduce their temperatures when adiabatically demagnetized. Let us say that I have a paramagnetic material and I suddenly expose it to a very strong magnetic field. So, the atoms of the paramagnetic material align themselves in the direction of the magnetic field. This is an exothermic process, that means during this process the entropy of the material reduces and heat is rejected. Okay. So, this is and the reverse effect, that means suddenly if I withdraw the magnetic effect, then the atoms get realigned to the original orientation, and this is an endothermic process, and during this process entropy of the material increases. Okay. So, as a result the material absorbs heat from the surroundings, the surroundings get cooled, and if you are not providing any surroundings or if it is isolated from the surroundings, it takes heat from itself, that means the temperature of the material itself drops, right. So, the principle of magnetic refrigeration is that you alternately expose the material to strong magnetic field and withdraw the magnetic field. Okay. So, during this process you can produce very low temperatures, temperatures down to absolute 0 can be produced using this method. Okay. So, let me quickly conclude. In this lesson, various methods for producing low temperatures were discussed. Practical refrigerant systems are based on one or more of these methods, and in addition to the above, refrigeration can also be produced by other methods which I have not discussed. These are namely thermoacoustic systems, pulse tube method, vortex tubes, etc. Okay. And the design and performance aspects of some of the common refrigerant systems employing the above methods will be discussed in subsequent lessons. Okay. Thank you.